Welcome to L1-zkEVM breakout call number one. For the newcomers, breakout calls are used in Ethereum to give a dedicated space to projects that are going to be shipped. Once the project is scheduled to be shipped in a hard
Do we want
fork,
to be recording? Sorry to interrupt.
I believe we are recording.
Okay, perfect.
Oh yeah, thank you. Yeah, so once the project is scheduled to be shipped during a hard fork, the breakout call then usually gets merged into the main governance call, which is known as all core devs. So the goal of this breakout call is to advance the roadmap that we set out earlier this year that you all saw in the planning document. That is, Stas, if you could put a link in the chat for people that want to look at it. This call in particular will just be used to give an overview of the different work streams in the planning document. And we're going to give space for each person who's been working on each individual work stream, about 3 to 5 minutes to just explain like what's happening. On shipping, we're aiming to have the work done by Glamsterdam, just because the main thing that's blocking is EPBS. And we're aiming to also ship it or propose it to be shipped in Hagata. So on that, I will start. So for logistics, we're aiming to have a monthly call on the second Wednesday of the month, 3 p.m. UTC. All async discussions, please put them inside of the ETH R&D channel. We have two channels for this. And on an announcement, the stateless team is hosting a stateless summit at ETHCCC on April the 1st. If you want to find out more details about this, just please scan the QR code. So just zooming out a bit to explain the difference between mandatory and optional proofs. So with mandatory proofs, all the attesters are required, all the attesters require proofs in order to deem a block as valid. Re-execution by them will likely not be possible if you want to keep up with the chain. This is a massive change to Ethereum. And so we're sort of doing this intermediate step known as optional proofs, which front loads a lot of the work and allows us to test it in a safer way. With optional proofs, only some attesters can opt into accepting proofs, but the majority of the attesters on the network will continue to re-execute as normal. This breakout call, just to be explicit, will be for optional proofs. We may touch on some mandatory proof topics, but the main goal is for optional proofs. Okay, so let's look at sort of what happens within a slot post-Amsterdam, but pre-ZK. And we're using this to sort of motivate the work stream breakdown that we saw in the planning document. I've split it into two phases. So phase one involves the builder, proposer, and a tester. The builder proposes an execution payload, which is a block or EL block. They then submit something known as a bid, and a bid commits to the execution payload plus some value that the builder is putting on the execution payload. The proposer for that slot then selects a bid. It can, because multiple builders will be publishing bids. They produce a beacon block and they submit this beacon block to the network. The attesters then validate the beacon block, produce attestations, and submit these attestations to the network. So this is the first phase. One minor note that might be interesting to folks who have never seen EPBS before is that once the attester validates the block, the builder's balance is unconditionally reduced. So if he says that he's bidding 5 ETH, 5 ETH is unconditionally taken from the builder's balance. The second phase, if you have seen EPBS, you can see that I've like massively simplified this part by removing the PTC. But the second phase, for our purposes, the builder then submits the execution payload to the network. The attesters then validate the execution payload. And for this, they obviously need an execution layer client. I'll be taking questions at the end, by the way. I can't see the chat. Okay, so what's the problem with this? The main problem is that the attester needs an execution layer client in order to validate the execution payload. What this means is that as the gas limit increases, it's going to take a lot longer to validate that the execution payload is correct, which means the attester's hardware requirements have to rise in order to do it in the same amount of time, which obviously leads to centralization pressure. Like as you increase the hardware requirements and the bandwidth requirements, it becomes harder to be an attester. Okay, so how do zkVMs actually solve this issue? Let's go back to phase one. Everything is the same apart from this new object called an execution witness. Phase two changes massively, and I'll give the caveat that there are many design decisions that we can make here. Like if the builder is the prover, you can imagine there's just one box here. If the prover is now a known entity in the protocol, you can imagine the prover sort of sending to the attester directly. But with this current design, I'll explain how it goes. So the builder selects guest programs. Ignacio will say what these are. They then submit an execution witness that they produced in phase one, the execution payload, and the guest programs to this new entity called the prover. The prover then creates proofs based on the guest programs, execution witness, and the execution payloads. He submits these zkEVM proofs to the builder, and then the builder then forwards it to the attesters. The attesters then selects guest programs independently. If the guest programs that the attester selects and the guest programs that the builder selects are different, then the proof will not verify. So the attester selects the guest programs. They then use the bid that they received from phase one and verify all of the zkVM proofs. So the guarantees that they get here are more cryptographical, but essentially, if they verify the zkVM proofs, it's roughly equivalent to them validating the execution payload by re-executing. Okay, so now these are if you've read the document, these are the eight projects that we've split, or eight work streams that we've split the work into. The first is this execution witness object. We want to spec it out and optimize it. So this is the first object that the builder produces in phase one and submits to the prover. The second is the guest program that needs to be proven. The third is this API boundary between the zkVM and the guest program and standardizing it. And Marcin will talk a lot more about this. The fourth is the consensus layer. So we need to make changes on the consensus layer in order to accept proofs and other sort of infrastructure changes. The fifth is the prover infrastructure, so the actual software that's creating the proofs. The sixth is benchmarking and metrics. So this is related to RTP, but also it's metrics and benchmarks for the consensus layer. Like if we submit these proofs on the network, how long does it take for the 66% of the network to actually see these proofs, since they are quite big at the moment. And the seventh is security, which Cody will go into more details about. The eighth is like an external project that we're not focusing on, which is EPBS. The reason is because we can't actually do this without EPBS. We need enough time to create these proofs. Currently in Fulu, which is what we currently have on Ethereum, it's about roughly 2 to 4 seconds, which is obviously not enough time. Okay, so with that, I will start taking questions before we go to Ignacio, who will talk about the execution witness and the zkVM guest program. I'll just check the chat. Oh, thanks, Will. Oh yeah, sorry. Also, ETH proofs is at ETHCC. Yeah, sorry, I didn't put it in my slides. There's a link in the description uh, for how you can register for beast mode. Okay, so the first question is, what is the expected size of the zkVM proofs? So currently we're looking the current the best case is it's 128 kilobytes. we're currently focusing on 300 kilobyte proofs, but I believe some zkVMs are well above it within the 600 kilobyte to 1 megabyte size, though this is expected to go down. Is there any incentive mechanisms for provers? So with optional proofs, because the majority of attesters won't need proofs, there is no incentives for optional on the optional proof regime. With mandatory proofs, we're still going over sort of what the incentive mechanisms will be for provers, as in whether they should be in the protocol or provers.
Abbiamo sentito urlare da sotto. Ero preoccupato ancora.
Emiliano, could you mute?
Sorry.
Thank you. Yeah, so the incentive mechanisms for provers, we're still going over. Julian is the one that's focusing on this, Julian Marr from RIG. It really depends on how we think provers are going to be integrated into the protocol. What do you expect the average proof verification time to be? Currently, so far has done a lot of measurements on this, and currently it's about 70 milliseconds to 100 milliseconds. Okay, cool. Ignacio, do you want to get set up?
Yeah, sure. Let me share my screen. Can you see my screen?
Mm-hmm.
Cool. I will go pretty fast because we don't have much time, so sorry for that. So I will give a brief update on project number 1, which is this execution witness that we mentioned before. So before giving any updates, let's go to a brief review about what this is about. So here we have like the guest program that we are proving, and this guest program can be thought as a function. So all the information that is required should be received by parameters. These parameters are basically the new payload request, which is basically the execution payload. Then we have this execution witness that we are focused on. We have the chain configuration. So basically, this execution witness is all the information apart from the block that the guest program needs to verify the block, right? So this execution witness basically contains all the state tree access state with MPT proofs, because we cannot really trust this input. So for example, if a block contains an is transfer and this load, we need to provide MPT proofs for the balance and the storage slot value. Apart from that, we also need to provide the bytecodes that were accessed in that block, because bytecodes are not part of the state tree today. This is going to be changed whenever we do code chunking, probably in binary trees. We also need to provide some set of ancestor headers, because we have EAP 2935, and also for block hash opcode resolution. So the idea here is that we want to standardize this execution witness and how is it generated, because ideally we want any EL client to be able to generate this with execution witness for a block. And this should work in any other guest program. So the situation that we want to avoid is only execution witnesses generated by Geth are only usable by a Geth guest program. Because ideally, if in production, for whatever reason, a specific EL has some bug or problem generating an execution witness, we want any other EL being able to generate a valid one that can be used for any other EL guest program. Also, this execution witness has many other border cases that we should properly test. So the only way to really create tests for this that all guest program can use is by having a standardized one. So here I have a really rough roadmap-ish of how we going to approach this at the spec level. I won't go into details, but I can share the slides later if you are interested. So the updates on this front are basically Peter from the Steel team is working on a generalized state tracker. This state tracker is required for the execution witness because whenever the block is executed, we need to track all the state that was accessed. This state tracker was already created for vals, so we are trying to reuse it and generalize it. The state tracker used for vals do not really track these ancestor headers and bytecodes that I mentioned before, so I already created some PR on top of his work to extend it. And I also did like a full end-to-end spec implementation of the witness generation, mainly to identify all the blockers that we might have whenever we try to merge all these in steps. Finally, I wrote a quick document explaining how OpenVM had another kind of way of expressing this execution witness that might be more optimal, that maybe we can use in the future in a new version. Cool. Since the next project is project number 2, I will move on with that. So this project number 2 is basically about having a standardized guest program in the spec that all the ELs can use as a reference to do their implementation. In the previous project, I put this guest program as a kind of black box here, but we really need to define what's going on here, because I think there might be some confusions that it's only like the state transition function, but we actually need to include more stuff here. So as a brief overview, you can think of the guest program in this way. So here we have the state transition function that people already assume it will be part of the logic, but we also need to include some other stuff like the engine API logic and validations that today exist in ELs. This should be part of the guest program because the entity that will be consuming this proofs will be the CL. And the CL today, like API boundary for the EL is the engine API. So we have to include logic here. Whenever we do blocking blobs, which is EIP 8142, we also need to do some extra work inside the guest program. And we also need to include some extra work regarding the output commitments that are needed for the verifier. As part of the state transition function, we need to do the execution witness validations. This is related to project number 1, because as mentioned before, the execution witness is not trusted data. So for example, all the MPT proofs that were provided should be validated. All the bytecodes should be checked against the code hash in countries leaf nodes. And the ancestor header should be checked using the parent hash in the blockchain. So apart from defining this guest program in the specs, which is the bulk of the work of this project, we also need to have reproducible steps to transform guest program source codes into the standardized targets. This is not only like the compilation steps, but ideally having a way to reproduce exactly the same ELF binary that EL clients will publish, because this is directly linked with the verification key that will be used by CLs. So ideally, we want anyone to reproduce this verification key from the guest program source code. So regarding the guest program in the specs, Mario and Peter from the Steel team are organizing a bit the steps that we have to do in the specs for this. There's a bunch of refactorings that should be done in today, because the way that the specs work assume that the EL client is stateful and has a database. So this should be generalized such that any state access can be set by a database or by the execution witness or something similar. So there are some steps to be done there. Then there were some progress by developer Uche regarding gaining more confidence that the current guest programs that we have today are reproducible in the compilation, and also include some signature inclusion because this will be part of the distribution process in the future. And regarding client updates, Ivan from Ethrex have also made progress on the ELF distribution pipeline. And they have been doing also some guest program refactors. All these things are links that you can click on them, and whenever I share the slides in the chat. And finally, I implemented this EIP 8025 for Ethrex and REST, mainly because all this engine API stuff required for the checks is done in Rust, and both clients are in Rust, so there's kind of some synergy there. This is a pretty big EIP to implement, but I left some comments in the PR that maybe our real clients might want to look at. So yeah, that's the end of project number 2. I will come back again whenever I share progress about project number 6.
Any questions for Ignacio? And while that's happening, Marcin, if you could start sharing your screen for project number 3.
Okay, can you hear me?
Yes.
So hi everyone. Today I'll share 2 threads of work that I've been focusing on. The main one is zkEVM interface standards. We just released version 0. This is about creating a common foundation for how zkVMs integrate with execution clients. The second smaller project is exploring whether we can enable languages like Go and C# to compile to bare metal zkVM targets via WebAssembly. So let me paint the picture of what execution client teams were facing before we created those standards. Imagine your execution client team preparing for zkVM-based proving. You look at the landscape and see multiple VMs, SP1, ZISC, RISC-0, OpenVM, and so on. Each one requires custom compilation targets. Each has different precompile interfaces. Each handles I/O differently. This means if you want to support 3 zkVMs, you're potentially looking at 3 completely separate integrations. That's a lot of duplicated work and maintenance burden. So to address this fragmentation, we've created 3 initial standards in collaboration with multiple zkVM teams. The first standard standardizes the RISC-V target triple for zkVMs being used on Ethereum. The second introduces a C interface for precompiles, and the third is a C interface for doing input and output. Let me dive a bit deeper into the first standard. So RV64IM is the 64-bit RISC-V instruction set with integer, multiplication, and division, and that will be a baseline for our architecture. On top of that, there is a requirement for unaligned access extension, and that's interesting. Now you may ask why we care about misaligned accesses, and it's a pragmatic safety net. So if a compiler mistakenly produces misaligned accesses, execution remains correct, possibly just slower with that extension. This prevents subtle toolchain differences from becoming consensus and liveness issues. The second standard addresses the issue of calling precompiles. Ethereum's EVM has precompiles which are expensive to prove using standard RISC-V instructions. So zkVMs implement them as optimized zkVM specific circuits. Without the standard, each zkVM has a different way of calling those precompiles. Our C-based API solves this problem. Execution client teams can write their precompile calling code once and then switch between zkVM backends without invasive refactors. The third standard is about I/O, how guest programs communicate with the outside world. They need to receive private input data from the host and also commit to public outputs that verifier can check. The C-based API provides two simple functions for this task. Those functions are tailored for zkVM needs and optimized for performance. Now let me switch to the second work thread, which is about expanding language support. Right now, if you want to write code that runs in a zkVM, you're basically limited to Rust and C++, languages that can compile directly to bare metal RISC-V. But what about Go and C#? These languages are also used by client implementations. We're exploring one possible way of bringing these languages to bare metal platform. We compiled those high-level languages to WebAssembly first, then compile that WebAssembly files into RISC-V bare metal. The question is whether the performance penalty of that intermediate step is acceptable. Initial benchmarks of the WASM approach for the state transition function in Go shows about 3 times instruction count overhead compared to direct compilation. But here's the thing, instruction count doesn't tell the full story when you're talking about zkVMs. Normal RISC-V instructions have different proving costs than precompiles. So the next steps are to integrate those precompiles accelerators and measure actual proving time, not just instruction count, to find out more about WASM approach for compilation of high-level languages. Let me wrap up with a bigger picture. So the 3 standards reduce integration complexity for execution client and enable fair comparisons between different zkVM implementations. And the language expansion work, if successful, could open up alternative ways of compiling high-level languages, which is good for diversity and resilience. All of this work is open source in the zkVM standards repository and WASRISC repository on GitHub. Please review the standards if you haven't yet and share your perspective. Thanks.
I can read out any questions if there are any in the chat. None. I think one point to make here is that I don't know if Leo is in the call, but they've been working a lot with WASM as well, in particular WAMIR. So we might see some stuff that integrates well with that. It's a bit different since we're compiling WASM to RISC, but possibly you can go from WASM, just proving the WASM directly, or converting a WASM to WAMIR and then proving that. Okay, Guillaume.
Yeah, it's a side question based on what you just like you just mentioned Powder. Powder wants to have automated precompiles. How does the C interface project takes that into account? Like I know for our WASM project we would like to use the automated precompiles from Powder, at least see how good it is. Yeah, it seems to be at odds with that other project of having yeah, like C headers for the precompile. So I'm just wondering how do we reconcile that?
Right.
Oh.
Yeah, so the idea is that each zkEVM vendor will have to implement that C interface that is standardized, and the application logic won't have to change. So basically, the implementation of precompiles will be provided by zkEVM vendors, and that will be resolved at the linking stage of the program. So the program will have to be recompiled with the correct archive for precompiled implementation, as well as for the implementation for I/O. But the logic itself, whether it's in Rust or C or C++, or other language that can bind to C, the logic won't have to be refactored or changed. So that's the idea. So basically, the idea is that the implementation of the C interface is provided by zkEVM vendors.
Maybe some context. We have about 2 minutes remaining for this section, but maybe some context on this precompile notion and what Guillaume was talking about is that currently zkVMs essentially provide an API for accelerating certain algorithms, so like CatChack or ECDSA. And there's a C interface that we've standardized on that allows the guest program to access these. But these are sort of fixed precompiles and they're fixed circuits in the zkVMs, while auto precompiles can be seen as sort of an automatic way where they look at the guest program and then they figure out, okay, what can we do here to speed it up based on this particular guest program instead of having these generic precompiles. I think it might require a bit more investigation, but my feeling is that we might not need the C headers for the precompiles if this is the case. Leo, do you want to opine on this?
Yeah, I think just in the auto precompiles case, what you can do is basically the guest can just choose not to use like the C interface or any precompile interface from zkVMs, or choose a specific subset, for example, that auto precompiles may be performing badly, for instance. And then so you can choose which ones you want, you can choose none, or you can choose all. So I think this would be the easiest for a guest that wants to use auto precompiles to just basically then just not use the precompiles that might be working well already with auto precompiles.
Okay, cool. Yeah, just to keep with time, maybe we can discuss this on Discord as well. Tao, do you mind sharing your screen?
Yep. Can you guys hear me?
Yeah.
Cool. So yeah, I've been working on the consensus layer integration. And in this talk, I'm going to essentially give an update on the specs, and finally the progress on the Lighthouse implementation. So to start off, just want to give a quick refresher on the engine API. So the engine API is essentially the API that the consensus layer uses to interact with the execution layer. And the new payload request is essentially the data payload which is used in the request. So when the consensus layer receives a new beacon block, it constructs this object, the new payload request, which contains the execution payload, the version hashes, the beacon block, parent beacon block, and execution requests. And essentially, it asks the execution layer or the execution engine to verify that it's correct. And some of these methods require the full execution payload. So that includes the transaction data. So the main takeaway from this slide is currently the execution layer requires full transaction data to kind of verify the new payload request and to assert that the new payload is valid. So ideally in the future, we want to kind of remove the requirement for zk testers in which they would need the transaction data. So the idea is essentially we move this to the kind of, we move the abstraction for the prover from kind of just the execution of the block to this, to verifying the whole new payload request. So essentially it's the same checks, but it outputs the new payload request route. So that is essentially just the hash tree route of the new payload request. And inside of the proofs, inside of the prover, we do all of these kind of consistency checks to assert that the versioned hashes, so the KZG commitments for the blobs and the execution requests are consistent with the transaction data. And then in regards to verifying the proof, the public input moves to this new payload request route. So let me move to the next slide. So here we can see the relationship between the data types which we have in the consensus specs for optional proofs. So there's a direct mapping between the new payload request and the new payload request header. What's nice about this is they ultimately hash to the same route. So you can replace the execution payload with the execution payload header, still construct the same public input. So yeah, ultimately that kind of just provides a bit of context on the guest program modifications that Ignacio touched on. And then in regards to the signed execution proof, this is the proof type that is gossiped over the network. We have the actual execution proof. We have the validator index. So just to provide context, we're going to use signed proofs because if we had unsigned proofs, then people could just send around a bunch of invalid proofs. They take 100 milliseconds to verify, and you can just grief the network. So yeah, the idea is essentially to use the validator set to sign these proofs. And the execution proof contains the proof data, the proof type, and the public input, which is this new payload request route. So we introduced the proof engine, which is essentially kind of analogous to the execution engine, but instead of working with kind of the new payload request or the full execution payload, it works with the new payload request header and the execution payload header. So we have verify execution proof method, we have new payload, notify new payload header method, and request proofs method. So yeah, I'm going to run through a few flows and to kind of show how the proof engine integrates. So we receive a new beacon block, we extract the new payload request header, we then invoke this method on the proof engine. So we send the new payload request header, the proof engine caches the header such that in the future, when it receives proofs, it can kind of, correspond them with this new payload request header. And then it returns syncing, and the beacon node will import the beacon block optimistically into the fork choice store. Then when we receive execution proofs, we receive them over P2P. We look up the validator index, which was included in the signed execution proof. We verify that the signature is correct according to the proof message, which is the execution, which is the execution proof itself, essentially just a hash of the execution proof. And then if that's successful, we invoke the verify execution proof method on the proof engine. We check if there's sufficient proofs. So we've got a K of N requirement. And if so, we communicate valid back to the beacon node, and the beacon node will mark the block as valid in the fork choice store. So previously it was marked as kind of optimistic, but now it can mark it as valid and say that this block is ready to be attested by the validator. And then finally, we rebroadcast the proof. And then in regards to proof generation, so the idea is that for optional proofs, we don't have this requirement in which the builder has to generate the proofs. So in the interim, we'll use validators to fulfill this responsibility, or some, it's opt-in essentially, this role. It's not required. But they'll observe a new beacon block. They'll extract a new payload request. They will then invoke this request proofs method on the proof engine, specifying the new payload request which needs to be proved, and proof attributes, which is essentially the different proof types. So the different provers that need to be invoked. It will receive a proof generation ID, and then the proof generation happens asynchronously, and they are sent back from the proof engine to the validator, who signs them and subsequently gossips them on the execution proof topic on the beacon node. So in regards to the proof gossip protocol, we had two requirements in which we don't want there to be a fork. We don't want there to be that's the primary constraint, essentially. We don't want there to be a fork, and also we can't slash for invalid proofs. This is kind of the construction we decided on. I should note that these specs may change. They're not kind of firm. Essentially the validator signs the proof and then broadcasts the proof on the execution proof topic. Nodes will ban peers if the peer has sent them an invalid proof, and they will ban validators. So essentially, if they ever receive a new proof signed by a validator which previously sent them an invalid proof, they will not even try to verify it. And one of the problems with that is consensus, because a validator could send a valid proof to validator C and an invalid proof to validator B. Validator B would reject the proof, validator C would accept it. So the idea is that validators will re-sign the proof with their own validator key, essentially. So then we kind of move to a. Sorry. Yep.
Sorry, just putting the timer up that we have 1 minute, just in case.
Yeah, I'm nearly done. That's the general idea. It's re-signed and sent to validator B. And then the assumption is just one of n. So you have one validator on its validator that re-signs and propagates the proof. And in terms of the Lighthouse implementation, we've implemented the proof engine. The proof gossip is implemented. We've done the kind of signature verification stuff. We've introduced a new service on the validator for kind of doing this signing and requesting of proofs. Done the integration between the beacon chain and the proof engine, and unit tests have been implemented. And then we have a few more bits of work to do, but made some decent progress there. That's all.
Are there any questions for Tao? Manu, if you want to start sharing your screen. Manu is a developer from Prism.
Yes. I think you have to. Okay, yes, I can share now. Oh, sorry. Okay, I'm sorry. I have to close Zoom and to reopen it again. So I won't share my screen now. Yes, very basically. We had June Song and developer Uch created an initial POC, proof of concept on Prism. And then we are currently adapting the code base to the latest specification, which is post the latest pull request on the spec. And so to help testing, I implemented a standalone Golang dummy prover, which was inspired by the one done by Kev on Lighthouse. And so just basically this dummy prover listen to beacon blocks from SSE and creates just a dummy proof. This dummy proof doesn't do anything. I mean, it's just an empty thing. And yes, and the prover publishes dummy proof to a beacon node via the new execution proof beacon API. And yes, and also I modified the kurtosis package, Ethereum kurtosis package to add the prover directly to connect the prover directly to a beacon node. And I will share my slides just in the chat. And yes, the big thing still to implement is sign execution proof, the sign scheme, which was not really doable with the current state of the spec, but I saw that Francesco modified this, and I will talk to him about the new scheme about signing proofs. Thank you, sorry about the slide sharing, and that's all for me.
Thank you, Manu. Yeah, it's pretty good that we'll be able to have a Lighthouse and a Prism implementation soon TM. Han, do you want to share your screen?
Sure. Can you see my screen? So I would give an update to the proving infrastructure project. I will focus on the array and zk boost and how we use them to provide the execution proof to the consensus layer. So in this project, there are three major repo that are used. The first is the array, which integrates various of the zkEVM SDK to provide a unified interface for use. And it also provides the Dockerized images, Dockerized compiler and server images. The server here is just a HTTP wrapper for the prover. And the second repo is the array guest, which provides the execution layer guest program, and it published the compiled ELF. And the third repo is the zk boost, which is the actual component that interact with the consensus layer. And inside that, it has two components, the execution witness entry and the zk boost server. And the execution witness entry and the zk boost server are essentially the relay and proof engine that Francesco just introduced. So I will skip the end-to-end flow here. And in the zk boost server, we have the example script to spin up the whole stack for Lighthouse, so we can test the proving infra easily. And so far, we have integrated the following zkVMs, and some of them support GPU proving. And here, the multi-GPU means that we can proving on multi-GPU, but on the same machine. And in the array guest repo, so far we have this execution layer guest program available, which allows us to provide multiple execution proof with different zkVM and execution layer combinations. The next step will be fully integrate the whole stack into the Ethereum package, so we can test the proving infra more easily. And also, I would need to clean up a bit to follow the EIP 8025 spec and naming, and add more metrics to track the pipeline efficiency. Yeah, that's my update. Thanks.
Thanks, Han. There are no questions. Okay, I think Stefan is sharing now. Justin made a comment, we should consider integrating zk boost clients into CL clients. Yeah, I think that's a good direction. Cool. Okay, Stefan.
Yeah, I didn't want to interrupt. I just wanted to test if I can share. Can you see the screen, I hope?
Yeah.
Perfect. So I just gonna give a quick summary what we've been looking into with the CK team and East Panda Ops. So we looked at building versus buying versus renting. And there's the option either to build the server ourselves and then put it in a co-location, to buy a pre-built server, or just to rent from a cloud provider. And here is kind of a overview, of course, the do-it-yourself is still the cheapest, even though the RAM prices have exploded. I'll go through it quickly, but we can talk about it in more detail if you want later on. And then kind of the idea is to have 2 clusters. And right now, this would be how it would look like if we did just the do-yourself build. So we would have 4 GPUs per server, and then 4 servers would be 1 cluster, and we would have 1 development cluster and 1 production cluster. That would be the idea right now. And these are just some requirements for the setup that we're looking into. I'm not going to go over it in detail. This would be kind of the setup that we're looking into. So just for 5090 GPUs, it would be good if we can get them to be 3.5 slots or smaller. We kind of looked into having the Asus version because they have pretty good cooling, but we have to look in that the heat gets pushed out of the back and not just to the side. So we're still investigating here what is the best 5090 version. 5090 is considerably cheaper than the 6000 version. But we saw that the 6000 RTX 6000 Pro Max Q version, which is just 300 watts, which is significantly less than 5090, is less performant, but only by 15%. But it's unfortunately so much more expensive as soon as you get into the enterprise market. And then for the CPU, we thought about the Threadripper Pro. The newest version was 32 cores, so we get at least 8 cores per GPU, and it has a lot of PCI lanes for all of the GPUs. And then motherboard, just a fitting one with enough DIMM slots. So we calculated also for the RAM that we need to use all of the slots so that we can use all of the bandwidth of the PCI 5.0 16 lanes. Which is, I think, around 256 something gigabytes per second. And with just 4 slots of RAM, we wouldn't max out the total. But with 8 slots, we would be able to utilize the full bandwidth. And storage is not that important, but we would want 100 gigabyte networking between the individual servers so that we can copy between them, because 4 machines would be in parallel working on the proof. That's kind of the setup. Here are some comparisons between pre-built systems that we also looked into, but I'll skip over that for now. And let's maybe look at the comparison. So doing it ourselves for a 3-year ownership would be around 570 in a co-location. We already got some information from the co-location, how much the setup would be and how much the monthly cost would be. And here it compares it against kind of the pre-built cheapest, the pre-built average, and the cloud rental. If you just rent for those years, even with a 5.5% discount, it's considerably more expensive. And you also don't have any amortization of the hardware. And at the end of the time, you don't actually own any of the hardware either. So that's also something that's not reflected here. And yeah, here's just kind of the co-location hosting breakdown from the offer that we got. So it's around operating around 8,500 a month. There's a 16,500 setup cost. And then you can see there the total cost operating without the hardware as well. And here's just a nice overview. I will share the slides as well. How much just renting versus doing it ourselves would cost over time, and where kind of the total cost of ownership break-even point is. Yeah, so the recommendation right now would be not 100% what this slide shows, but kind of this is the general direction. So we could also do like a hybrid approach. So either just go all in with this do-yourself build, or choose a pre-built. We haven't 100% decided yet. This is just a recommendation. Or we can do a hybrid where we just get one do-yourself build 16 GPU system in the beginning and then rent the other one. That's still kind of up for discussion. But I hope this kind of gave you a little bit of an overview. And here just the appendix, kind of like what CPU to choose. And any input or anything would be great if you saw something that might not match up in this presentation. But I think that's pretty much it from our side.
Thanks, Stefan. Yeah, so for people on the call, we may run over by 5 minutes, just because I didn't keep time properly and didn't expect the questions. If you need to leave, these are being recorded, so it's like completely fine. The next one will be George from the security team, the cryptography team.
Hello guys, let me share my screen. So I just want to give an update on the zkEVM security sprint, an initiative we launched late last year with the goal to bring zkEVM security to 128 bits this year. So we plan to do this in 3 milestones over this entire year through an iterated process with the teams. But today, I mainly want to talk about this update blog post we pushed today on the zkEVM team website. And it does 3 things mainly. One thing is that it presents a visualization of the timeline and the milestones and stuff for people who are more of the visual kind. So you can see this thing here. And also for the first milestone, which is at the end of this month, the SoundCalc integration. After talking to teams, we would like teams to also integrate their inner segment lookups into SoundCalc, because that's a big part of the soundness of the segments, which is the first thing we want to start looking at the proof system security. So this is one update that we want the lookups integrated. Many teams have already done it. And the other update is that we published details on the zkEVM architecture white paper, the documentation effort we want to start. So if you see here, we have a PDF with how we expect this document to look like. Again, it's going to be done in an iterated manner and with different milestones. And now you may start understanding why the visual representation is useful. So yeah, please check out the document on how we expect the white paper to look like. If you have any questions, let us know. And yeah, thanks a lot. I think, who's next, Kev? Maybe it's Cody.
Cody. Could you drop a link to the post as well, George, in the chat?
Yeah, absolutely.
All right, you all should be able to see my screen. So this is a report on Project 7, which is the sort of meta project of security. A lot of what has already been spoken about is relevant to security. What I did was take the description on the planning repo and try to map it out into some smaller set of higher level goals. This is the planning repo, and either implicit or slightly missing from the diagram that I'll show on the next page are some of these things. So the audits and bounties, prover incentives, security of the supply chain, which was touched on in terms of like reproducibility of guest program verification keys. And another issue that was raised in the planning repo is relating to security of provers if they are co-located, where maybe the fact that GPUs are shared with the public could lead to sort of starvation of those resources, and that's related to prover liveness and incentives. Some of that stuff can be wrapped into the bars on the following page, which is supposed to be taken with a grain of salt. It's not exactly time consistent, because I took some things that are mapped out exactly in time, like what George just spoke about, where there are specific deadlines, and tried to lay them out with things that are still a bit fuzzy. But I think still it's useful to have a look. So yeah, we aim to have optional proofs in Hegata. And sort of that itself is a bit of a fuzzy deadline, but working back from that, this is, I don't know, these bars could be something like a month and a half. Purposely, they're not laid out in dates. But I imagine grouping the initiatives into the sort of initial affirmation grouping. I actually don't know if you can see my mouse. I hope you can. But at the top left, we have a kind of like reaffirming hardware requirements, writing down a threat model. That's something I've started to do and we'll reach out to people about and share on the next call. But some of this initial setting of the stage and really getting consensus once and for all behind some of these things. And then we need to also, on a slightly longer scale, figure out what is a minimum set of tests that we're happy to launch optional proofs with. And also what exactly we want from the specs of these zkVMs. For instance, the consensus clients should contain, or the consensus specs should contain specs for the zkVMs, but we would like other specs. And there's also this notion of the white paper spec that George and his team has asked for. And I put some of the cryptography team's goals on here. So we have the SoundCalc integration and due pretty soon. And the next phase, we work to improve security of the proving systems, thinking about the diversity strategy where we have many proofs to be verified. We want those proofs to be uncorrelated, in terms of, say, dependencies for the guest programs and the provers. And we want to also start to think about which zkVMs, how should we choose which ones will be whitelisted, what that looks like. And yeah, also, I guess, validating by building out these clusters that Stefan just spoke about. We need to make sure that those hardware requirements are viable. I mean, we have a lot of data from ETH proofs, but it's good to be have an say at least EF internally building some of this stuff and feeling really confident about that. And then at this point, yeah, we can make some decisions. And then in the next phase, we work even more to improve security of testing, building some monitoring, making sure that everything is reproducible, working on specs, improving security of the proving systems. And then at some point, we have to choose which zkVMs, EVMs we're really confident about, and what is a good diversity requirement. It might not just be K of N, because if some set of K is highly correlated, that maybe is no good. And then we have this phase where we think about incident response. We have to monitor for stability, and we need to sort of test out our incident response and look at the specs. So yeah, then for mandatory proofs, well, like the scope of this call is not really on mandatory proofs, but since it was represented in the planning repo, I mentioned here some additional or expanded requirements, specifically calling out formal verification as a likely requirement for mandatory, but perhaps not for optional. That doesn't mean we won't have significant formal verification in place, though, before optional proofs. And yeah, so what's next? Well, I'll keep track of this stuff and keep track of ownership of these things in a loose sense, and report on progress in these calls. And we're making monthly updates to the planning repo, and we should discuss in these calls and also on the ETH R&D Discord. That is all for me. Thank you.
Okay. Thanks, Cody. There are no questions. Ignacio will give his talk in the next breakouts, just to give more space for this one. And then we have Alex H and then Farah from ETH Proofs. And then we can close out. Yeah, thanks guys for staying on.
Yep, I'll quickly share my slides. So my slides are also in the chat. If anyone wants to have them for later, there are links to the website and there are links to the Telegram group where some of that work is discussed. So it says I'm screen sharing, but I can't see that I'm screen sharing. I don't know if Kev, you can confirm. Okay, perfect.
I see
we're seeing the Zoom screen.
Oh,
yeah. It should be fine now. Okay, so anyway, there's this big form verification project. I'm going to try to speed through quick updates. There was 2 tracks. There's the RISC-V zkEVM track where we're looking at the circuits, in particular the RISC-V circuits and precompiles. And as part of that, the cell RISC-V specification. There's the EVM track where we're looking at kind of the guest program, EVM, STF running on RISC-V and trying to assess that that is running on RISC-V and compiled to RISC-V, ideally bug-free in a way that can be shown equivalent to a formal EVM specification. And there's a cryptography track, which is about specifications and formally verifying the proofs of security for the proof systems and kind of cryptographic primitives, which are used by zkVMs. To give a quick update on every track, for the zkVM track, we have some reasonably short-term targets. So we've now finished extracting the official RISC-V cell specification to lean. This is a general purpose cell to lean extraction. It supports every RISC-V extension. It supports every other ISA that is defined in cell. For that matter, though obviously we haven't kind of tested this as much. There are also extractions, for ROC and Hawthorne, Isabel, other proofs of systems. We're not using them, but in principle, they're useful. I think the ROC one in particular is fairly polished. We've been able to use this specification to get proofs done for the RISC-V circuits of several zkVMs. This includes SP1, although memory consistency hasn't been verified yet. That'll happen. It includes OpenVM. They released this week. Congratulations and big thanks to both of these for obviously taking the initiative and co-funding this. We'll be obviously doing this with the other zkVMs, kind of ideally ahead of Amsterdam. There is no kind of specific preference in ordering. It comes down to when teams have felt ready to do it in terms of having stable circuits and things like this. And just a quick note, there are some assumptions that are done regarding lookups, which is that the semantics of the lookups are correct and things like this. We'll try to address these as much as possible, maybe before Amsterdam, maybe after Amsterdam, but certainly before Amsterdam, we want to have kind of zkVMs that will have their constraints for the different opcodes and memory consistency checks on all of this all done and in a state of maintenance. We're also looking at precompiles, of course. We are able to verify precompiles in the same way that we verify RISC-V constraints. For example, one highlight has been verifying the Plonky 3 Keshak in ROC, actually, not in Lean. And we can do more precompiles. The main issue with precompiles is that we have several zkVMs. They all have many precompiles. Verifying them all is doable in principle, but a bit of a time sink. And there's a bit of uncertainty regarding how many precompiles a zkVM is going to have. So we're just looking at maybe how to scale this, maybe how to use precompiles written in Lean, which are easier to verify. We'll see what to do with that as we get close to Amsterdam and around that time. We're also verifying order precompiles, with Powder and Satora. This is ongoing. I think order precompiles are great. I hope this helps, drive the adoption of order precompiles, which seemed like it would also solve the issue of having too many manual precompiles to verify. There are a bunch of miscellaneous other things going on. We have lead DSLs for circuits, which are able to define precompiles and actually prototype VMs as well at this point. We have L1-zk, which are these MLIR, family of MLIR DADEX for both constraints and witness generation. These are all ongoing. There were kind of SMT backends, Lean backends verified, being developed for all of this. I won't go into detail here. For the EVM track in 2025, there was a tooling developed with runtime verification. We're able to verify that the execution of opcodes on RISC-V, that is taking RVM or RVM interpreter specifically and compiling that to what at the time was the SP1 RISC-V 32-bit target, and then doing equivalence proofs since KVM was doable. This hasn't been updated yet to the new 64-bit RISC-V target that is being standardized on, and we'd also want to see how to extend that to the guest program / STF as a whole, as well as obviously supporting more guest programs. There's an issue of this is kind of doable. It's unclear how robust the tool chain is. Different guest programs obviously produce different assembly that may be more or less nice to look at and deal with. And there's a question of balancing costs of doing all of this versus the assumptions that we're making about client diversity as a hedge against bugs, especially this year because budgets kind of EF-wide are somewhat reduced this year. And so I'm looking at this at the moment, and we'll probably have more of an update on this very soon. And same, there's a question about whether it makes sense to have a kind of canonical guest program, which would obviously be something that comes with very high assurance in the form of
a guest program that is generated from a formal specification and compiled via a verified compiler, and obviously ideally performant enough. Sorry,
your screen seems to be there is something
choppy. Okay, let me. I'll stop sharing and restart sharing, and that should probably be the fastest way to fix it. Okay, let me know if this is better. So yeah, the EVM track at the moment is a bit in flux because we also have many new guest programs and obviously the standardization at the RISC-V target. Now the cryptography track, also to go over that very quickly, this is a bit less shorter, maybe a bit more medium term, suddenly thinking of mandatory proofs as Cody had on his slides. We have RClip. This is a library of formally verified executable specifications to proof systems. This verifies everything down to the underlying coding theory. We are starting to have specifications in there. We have interactive fry, we have some check. We're also starting to have, fully executable specs. The goal here is obviously to be able to verify, in particular, the Rust verifiers. We have a tool called Hacks, which is being developed with a lean backend for this purpose. We're starting to use Hacks. We're starting to verify some Rust code with Hacks. There's a bit of a challenge in the complexity of features that are used in Rust libraries. By features here, I mean features of the Rust language, which have varying levels of support by Hacks, because we don't have formal semantics for Rust, obviously, and so that tooling has to be support for additional features is done on a kind of one-by-one basis, and can take a bit of time. This will be ongoing in the next year or so. It won't be done before optional proofs. We're obviously aiming to get it done, before mandatory proofs. And then on the kind of miscellaneous side, again, we're also looking at actually compiling our lean specifications to optimize the MLIR dialects and see if potentially if we just generate faster code than what is generated from Rust, and potentially we can verify actually these MLIR dialects because we don't need too many. Maybe we're able to skip verifying, Rust code in some instances in making our life easier. Again, this is ongoing, and especially this part is slightly exploratory for now. Just to wrap up, we have progress going on each track. There's a mix of short-term targets like the RISC-V circuit verification and the pre-compile to an extent that we want to wrap up, around Amsterdam time. There are more kind of medium long-term targets with specs for the proof systems, which obviously the proof systems now are more complicated than just Fry or just some check or whatever. And obviously trying to push for greater integration of formal verification in the development and testing process to try and make all of this smoother, and we're driving costs down, I think, for a lot of these formal verification tasks as well, which is one aim, obviously, to make this sustainable. We're aiming to be robust to changes in the stack, so that if people rewrite their circuits, change the guest program, whatever, we can handle this. Again, this comes down to kind of making this economically sustainable and putting upfront effort into tooling to make this happen. So yeah, well, I have high expectations that things like the RISC-V circuits can all be done by Amsterdam. We're not treating this as a blocker, because we can do optional proofs, I think, without this, if we happen to be delayed by a week or whatever. But I still expect this to happen regardless. And then we want to obviously use the optional proofs period to establish robust maintenance practices before we do mandatory proofs, because obviously maintaining the proofs, maintaining the link between the proofs and the software that's verified is something that is going to be a very important part of moving forward and handling upgrades and things of that kind. We have a website, verified-zkevm.org. It was updated a bit recently, so there's the grant list and recent talks and blog posts and all of this up to date. There is more documentation coming soon regarding more specific details of what was done on the different grants, as well as some maybe more researchy challenges and topics that indicate kind of some of the future work. There's also a Telegram group. There's a link here. There's a link to the slides in the Google Meet chat you can click on, and it's not the most active Telegram group. There are a lot of projects. Some have split up into other channels, but it's a good way to follow what's going on overall. That's it from me. I guess I'm happy to take any questions unless Kev says no, and we need to leave it here. But yeah, happy to also answer questions asynchronously on Telegram, email, Signal, whatever else.
Yeah, maybe take questions async.
Yeah.
Farah, did you want to?
Yep. Let me share my screen.
Yeah. Thanks again, guys, for staying on.
Yeah. So we're testing all kind of new zkVMs proving mainnet on ETH proofs first. So if you're a new team, we'll probably onboard you through the staging app first. So I'll drop a link to that in the chat. But if you come to the sign in button, actually, you'll be able to go through a sign up process. If you click on the sign up button here, it should load. And so you can basically sign up as a new team. I'll receive kind of a notification that you're trying to sign up, and I'll approve you, and you'll receive kind of a notification with an API key in the email. And then once you're a new team, you'll have a dashboard button here, and you'll be able to come into a dashboard and create a new zkVM. And so you could see once you're onboarding the security metrics and the performance metrics that you'll need to fill out. Once you create a new zkVM, I'll also receive a notification to review it and approve it. So you'll go into this awaiting review status. You can also make any edits to it, and I'll receive a notification to approve those too. And so then also you'll be able to create a cluster here once the zkVM is there, and you'll be able to then test the zkVM that you're onboarding with. Once you're approved, you'll come into this coming soon tab here, and the metrics you won't be able to see yet. But once you actually have a cluster and you're submitting a proof, you'll become active. And so then all the metrics that you filled out and that we're tracking, you'll be able to see here. And then we'll be tracking, you'll come to, when you're submitting the proofs, this API documentation will help you here. You'll actually self-report approving time that we track. That helps us also track the average cost. And then we do the total time to proof, where we're using the block time and the time that you submit the proof. And so we're tracking those things. So yeah, reach out to us on Telegram too, but I'll drop the link to the staging app in the chat.
Right. Thank you, Farah. We have a question. If a guest program team is not ready to be on ETH proofs yet, does it make sense to sign up ahead of time?
Yeah, I mean, I don't know why not. I think it's totally fine to sign up. Yeah.
Okay, cool. And yeah, you can reach out to Farah async about doing this. Okay, so we're about 19 minutes over time. Thank you all for staying on for the extra 19 minutes. This was the first breakout call. I would say please join the Discord, our ETH R&D Discord, to find out sort of what's happening async. A lot of things are happening between the monthly calls. And yeah, would be great to just talk with you guys. If that's it, I will see you in about 4 weeks.